Okay, so it seems that you can hear me in YouTube. So thank you very much for taking part to the test. It seems it was good. Many students managed to get 3 questions right, which I'm very satisfied of. Yes, it seems quite a lot of students achieved a good results. I will, if you don't mind, or generally speaking, I would like to have a small talk with everybody of you personally over MS Teams so that we can discuss about the results of the test, okay? So if you have any doubt about the questions, we can simply talk about that. Generally speaking, I'm satisfied. So I can see that maybe there is 1 or 2 doubts for each of you. So we will just have a small talk about the test to clear the doubts where there is maybe something which is not clear, okay? Fine. We can start with the lecture. Before going on the topics of the 8th lecture, I wanted just to very briefly address a question one of you made me by writing me an email this week. He made a very interesting question. He said, what about the sign of the offset voltage of an operational amplifier? In lecture number 4, we've studied the effect of the non-idealities of an operational amplifier when we use it, for instance, to amplify a voltage. And for instance, we have studied that if we have a real inverting amplifier, which means an inverting amplifier using not an ideal operational amplifier, but a real operational amplifier where we have bias currents and offset voltage, then the output is not only given by the input voltage amplified by the ratio R2 divided by R1, where R2 is the resistance in feedback and R1 is the resistance in the input, but there are also the contribution given by the negative bias current and the offset voltage. The negative bias current gives a contribution to the output, which is the current itself times the resistance in the feedback, R2. And the offset voltage gives a contribution which is amplified, which is the voltage itself, amplified times 1 plus the gain of the amplifier. And I told you this is very important to take into consideration because as you increase the gain of the voltage of the input, the gain of the amplifier, then you amplify the input voltage, but you amplify also the offset voltage. So this is not a problem that you can solve by increasing the gain of the amplifier, which is a common technique, because what you do typically, if you have a source of noise and you have a small signal, you amplify the signal to make it bigger than the source of noise. In this case, this trick doesn't work because if you increase the gain, you amplify not only the voltage, but also the input voltage, but also the offset voltage. And then he asked me, okay, what about the sign here? Should we care about it or not because it's just uncertainty? Well, if you see here in this equation, I wrote plus minus. Why? Because as a matter of fact, you don't necessarily know the sign of the offset voltage. And generally speaking, you don't even know the value of the offset voltage itself. If you go on a datasheet of an operational amplifier, typically you find a table with all the parameters, and you find the value of the offset voltage, which is marked as typical value. In this case, it's 45 microvolts. And then you see there is another value, 150 microvolts. These are the values of the offset voltage for this temperature at 25 Celsius. Then, of course, if you consider not 25 Celsius, the working temperature, but a wider range of temperature, for instance, if you want to use your device between 0 and 70 Celsius, you increase the maximum values of offset voltage that you might find. And even more if you select a larger temperature range. So from minus 40 to plus 125 Celsius, you get to a maximum of 330 microvolts. This doesn't mean that the offset voltage is 45 microvolts. This is a typical value. What does it mean? If the manufacturer of the operational amplifier is honest enough, they won't give you only these values, but they show directly the curve of distribution or statistical distribution of the offset voltage that you might find in your operational amplifier. It means that they take a bunch of operational amplifiers, I don't know, 500, 600, 1,000, sometimes even more if they want to give a very precise data. Then they test the offset voltage of every single operational amplifier, and they find out that they have a distribution where the offset is, they count how many amplifiers are in each bin of the offset voltage, and they plot this histogram, okay? This means that, for instance, I don't know how many amplifiers they measured in this test, but for instance, they found about 23 amplifiers which had an offset voltage of about negative 10 micro, but they found, for instance, only 7 which had 60 microvolts. As you see in this statistical distribution, first of all, you can have offset voltage which is both positive and negative, and generally speaking, it has a value which changes as almost as a normal distribution, a Gaussian distribution, okay? Which means that, generally speaking, if you have, good luck, you might have an offset, an operational amplifier which has very small offset voltage. But if you have bad luck, you might arrive up to 100 microvolts. So this number here tells you only which is the typical value. This is important because maybe I was not explaining this concept well enough when we talked about this topic in lecture number 4. But when you consider this equation, this doesn't mean that you can know the actual contribution of the offset voltage to the output. This is how the offset voltage acts. This is how much the offset voltage gives contribution to the output voltage. But generally speaking, you don't know this voltage offset. If you go to the data sheet, you can say, yes, more or less it will be about 45 microvolts. But it could be 10 microvolts as well as minus 100 microvolts. So you cannot go to the equation here and say, okay, I subtract from the input voltage this offset voltage here, because you don't even know the value, unless, of course, you tested it. Then, if you know the value, because you take your operational amplifier and you test it, and you know the value of the offset voltage, then it's not uncertainty anymore. It's about error. Why? Because you know the value, you tested the operational amplifier, you know the value of that offset voltage, and then you can make a prediction of the contribution of that offset voltage to the output. Okay, so you take your operational amplifier, you measure the offset voltage, and then you are able to calculate this contribution, okay, to the offset voltage, to the output voltage. In that case, you can make a correction of an error. This is not uncertainty anymore, because you know the value of the change in the output due to the offset voltage. You know it because you know the value of the offset voltage. Then if you know the output of the offset, the value of the offset voltage, you can recalculate the error introduced by the offset voltage to the output, and you can remove it. If you remember, it's the same concept we discussed when we measured, when we explained the methodical error that you have when you measure a resistance using a voltmeter and ampere meter. Remember, in that lecture, we said, okay, we have an ammeter, we have a voltmeter, and we want to measure a resistance, okay? But the voltmeter includes by itself its own resistance. So what you measure is not the resistance Rm, but you measure the parallel of the resistance of the voltage and the resistance Rm. In the very same way, if you move the voltmeter before the ammeter, you have here the ammeter. This is equivalent to have the resistance of the ammeter and the resistance Rm. Okay? So what I said is when you measure, when you calculate the ratio of the voltage and the current, you get the series of these two resistances and you subtract the resistance of the ammeter, which is the methodical error. Now, this, I said, is not an error. Sorry, it's not an uncertainty, but it's an error. Okay? So, if I calculate the voltage divided by current, I get the resistance of the ammeter plus the resistance that I want to measure. So, this is an error. And I can say that it's an error because I know the resistance of the ammeter. Okay? I can measure it. Fine. So in this case, when you know deterministically the value of the error or the value of the mismatch introduced to the output, then you can call it error because you can subtract it. But in most of the cases, you don't actually know the value of the offset voltage because you don't test every single operation amplifier that you are using. So what are you going to do it? If you don't know this value, this is not an error anymore. You have to basically make, sorry, let me clean here. You have to make some estimation of the value of the contribution of the offset voltage to the output based on the information you have from the datasheet, okay? So you can say, okay, I don't know how much is the offset voltage of my particular operation amplifier, but the datasheet tells me that it has this statistical distribution, okay? So since you calculate the standard uncertainty, here. First, you calculate the uncertainty of the ideal operation amplifier, and then you add other sources of uncertainty. What does it mean? It means that I don't know this contribution of the offset voltage, but I can derive it somehow. I can find the expected, the value at, or better, let me be precise here. I can give you a range of value where I can reasonably expect to find the actual contribution of the offset voltage, which is exactly what you do when you calculate the uncertainty. Okay? So, if I have this statistical distribution, I must find a value of the standard deviation. Okay? So I take this value. I take this histogram. Sorry. I draw an interpolation of the normal distribution of this curve. You see, it's with such limited data is not as normal as you might expect. So it's not exactly a Gaussian distribution. Sometimes it's asymmetrical, but it doesn't matter. Just let's be practical and give an estimation. So you take these values. You see that one standard deviation corresponds to about 45 microvolts. Fine. You can say that this offset voltage is about 45 microvolts. Okay. Then, if you have this curve, you can estimate. You can say that 45 microvolts is one standard deviation, and therefore, then you multiply it times the gain here, and you already have your value of the standard uncertainty. Okay. What happens if you don't have a statistical distribution? Well, in that case, if you don't know how is the distribution, the only thing you can do is to take is to assume an uniform distribution in the value of the maximum offset voltage here. It's not very symmetric, sorry. Let me do it again. So you can say that you have between minus VOS maximum and plus VOS maximum, you get a uniform distribution. Generally speaking, it's very unlikely it will be like that, but if you don't have any extra information, just assume an uniform distribution. And so that case is 150 microvolts or 250, 350, according to the conditions where you're working, according to the temperature. And then you go here and say, okay, I take the maximum value of the offset voltage, I assume it will be uniform distribution, and therefore I can take this maximum contribution to the output and divide it by square root of 3 to get one standard deviation. Okay? So the point here is both in case that you know the distribution and you take one standard deviation from the Gaussian distribution. And also, if you don't know this distribution, so you take just the maximum value and you divide by the square root of 3 to get one standard deviation of the uniform distribution. In both cases, here, what you do, it's simply to take this value as uncertainty. Now, maybe this student who made me the question was misled by my mistake here, because I put minus plus here, when in fact it should be inside the parentheses, which then becomes obviously only a plus because you have a square here. Because we always sum this contribution, since we sum them quadratically, we always have the positive sign, okay? So, so in fact, I must correct myself. I should put these contributions, this plus minus here, under the square, under the square root, okay? So here I have my uncertainty of the ideal case, which is this one, the one that we always calculated by taking the three sources of uncertainty, R1, R2, and B2, calculating the partial derivatives, and then calculating here under the square root. That is something we have done plenty of times. Then, if you don't know the value of the offset voltage, the only thing you can do is to say, okay, I consider it as an additional source of uncertainty, so I cannot subtract the value from the measured voltage at the output. You cannot take V2 here, okay, and remove this contribution, because you don't know the value of this contribution if you don't know the offset voltage. You can do it only if you know the value of the offset voltage, because then it's an error. But if you don't know this value, you cannot subtract it. If the only thing you can do is to give a range where you can expect reasonably that value to be, then the only thing you can do is to take this range and add this range of uncertainty to the other sources of uncertainty. Okay? And the same applies for other sources of non-idealities, okay? Okay, I hope this cleared up the reason. Oh, by the way, why do you have these different sources, different values of offset voltage? Simply because the offset voltage is given by a mismatch on the input stage of both the positive and negative input. And this mismatch is given by production errors, sometimes even by the packaging itself, giving different pressure to the chip. So sometimes the mismatch could be more on one side than the other, and vice versa. And therefore, you can have plus or more or less offset voltage in either direction. That's the problem, because if the offset voltage would be always the same, it wouldn't be a problem. You know it, it's always the same, you subtract it, and Bob's your uncle. Unfortunately, it changes as due to the manufacturing processes, so you cannot have always the same value of the offset voltage. And that's why you, unless you measure it, you have always this range, which you must consider as an uncertainty, okay? Fine. Now, let's go to lecture number, oh, no, not this one. This one, okay. Let's go to lecture number 8, sensors of velocity, acceleration, and vibration. Let me see here, okay. This is a lecture strongly connected to the previous lecture about measurement of position, because if you want to measure, for instance, velocity, one thing you could do, as I've already mentioned last week, is to measure the position s, and then calculate the derivative of s in time. You know that the velocity is the derivative of the position, so you can simply measure the position and then calculate the derivative. You can do it. Nothing prevents you to do so. But today we will study other methods. Methods where you take advantage of physical laws, where physical quantity depends on velocity. Okay? So in that case, you directly measure a quantity which depends on velocity in order to derive the velocity. Now, again, the principles are very similar and somehow very strongly connected to what we have already seen. So there's not much new about that, but it's quite interesting sometimes. I will introduce also some methods which are very useful for practical applications. For instance, let's take this electrodynamic sensor of velocity. The structure of the yoke is in fact very similar to what we have already seen last week. So you have a ferromagnetic yoke, which is used to take the magnetic flux produced by this permanent magnet and to make the flux circulate in this direction. Okay? And of course also in this direction. So you must imagine that this magnet here, again, I just cut half of the yoke to show how it looks inside. Just imagine that this magnet produces a magnetic flux which rotates this way and returns back to the magnet. Okay, so just imagine to have a magnetic flux which enters radially from all directions to the North Pole. Okay, so just think that here you have all a magnetic flux, if you watch it from the top, which enters radially or vice versa because it's the North Pole. And then we have a coil wound around this magnet. The coil is suspended on some hooks here with a membrane. So this coil can fluctuate up and down. So just imagine that you connect this membrane to the device you want to measure the speed of, and this speed moves this membrane up and down, making this coil move also up and down. Here is the flux which circulate as I described you before in the yoke. And then you have this coil which moves with a velocity v up and down. So the velocity in this case is vertical. Okay. Now you remember that if you have a conductor which moves with the speed v in a space where you have a magnetic field in this direction, then you get a voltage at the termination of the wire, which is proportional to the velocity. Okay, you have B, the magnetic flux density, D is the length of the wire, and V is the velocity. Okay. Now let's see what happens in this device. You can imagine every single section of this coil to be like a small wire. A small wire which has the speed in this direction. Now I flip in order to have the same direction as in this diagram. I flip the image, so it's 90 degrees rotated. So you have a wire in this direction which moves with this speed. And then you have a flux density which is orthogonal to it. In this case, you generate a voltage which symbolically is represented by this generator with this direction. Then, if you go all around the circumference of this coil and you arrive to this side, then the velocity is the same. The magnetic flux density is opposite, okay? But so the voltage will be reversed. But don't forget that these two generators are in series. So the voltage sums up, okay? So you get a voltage like this. Then, so here we have a voltage pointing in this direction, okay? Then when I return back from the other side, it will point in the other direction. And it will continue all over the coil. So you will have a voltage which totally sums up and gives you a voltage proportional to the velocity of this coil going up and down, okay? Another sensor of velocity is simply based on the same principle of the DC generator. If you studied electrical machine, probably you know how it works. We have two magnetic poles, which create a magnetic flux, and then you have a coil which rotates orthogonally to this magnetic flux. Okay. So what happens if you have a coil which rotates in this magnetic flux, in this magnetic field? Then, according to the angle of the coil relative to the direction of the magnetic flux, you will have more or less flux entering in the coil. Okay. So let me see if I can try to draw it in a decent way. So let's assume that we have this coil here, and you have the magnetic flux density. Talk about magnetic flux density, which enters in this direction. Now, from the top, I would see something like this if it's totally orthogonal, okay? Or something like this if you have some angle rotated. And in the worst case, I would have, let me draw it here, (90° angle, okay? In that case, I have much less flux, in that case, zero flux at all, okay? Why? Because I have to consider the projection. Okay, let me draw it better here. So if you have your coil, which is rotated, it's like if the actual width of the coil is not this, but this, okay? It's like if you have a narrower coil. If If you rotate it even more, then your coil is even narrower. In the extreme case, so it's like it's like if the magnetic flux doesn't see a coil this large, but this large, simply because it rotates and it looks narrower with respect of the magnetic flux. If you arrive to the extreme of 90 degrees, the magnetic flux is 0 because there is no flux which can possibly enter in a coil if it's aligned to the direction of the flux, okay? So by rotating, you see a magnetic flux which changes, not because the flux changes itself. The flux is always the same. It's generated by some DC permanent magnet. So the flux is always the same. What changes is the flux which can enter in the coil, okay? And therefore, it does depend on the angle, and as this coil rotates, it has some velocity, it will generate a voltage due to the fact that you have a flux changing in time, changing with the same frequency of the rotation of the coil, and therefore, if you have a flux which changes in time, you have a voltage which is in fact proportional to the angular speed of the coil. Okay, so in this case, you don't measure linear speed; you measure angular speed, angular velocity. Okay, fine. Now, there are other ways to measure angular velocity, and I've mentioned them last week when I was talking about measurement of position of angular position. In that case, simply you can measure with the magnet, for instance, or with, well, in this case with the magnet, you measure simply the induction on the magnetic sensor. In the other case, with some asymmetric ferromagnetic piece, which changes the induction on the induction sensor, or with reed sensor, with the decurrence. It's the same principle of, with the optoelectronics, the same sense of position that we have seen last time. In this case, you make, in fact, a measurement of position, and then counting how many pulses you get per minute, you can measure the velocity, the angular velocity from the position. So this is an indirect measurement. What you measure here is, in fact, the position, and then you derive the velocity, the angular velocity. Now, let's go to something more interesting, and which is the measurement of speed by means of convolution. What does it mean? Let's take this very simple example. Let's say that we are in a factory producing some casting some iron. So you have these huge bars of iron getting out from the furnace, and you want to measure the speed that they go on this conveyor belt where they are carried over the factory. Now, this is not easy to do because, well, definitely you need you cannot touch the device itself. You can use some optical sensor, for instance. You can say, okay, I have some source of light from one side, I have some receiver of light on the other side. It's not so easy because it might be affected by the radiation emitted by the ingot itself. And generally speaking, it's not a good idea if this bar is very long, because what you see, you need all the bar to go over to get the change from the beginning to the end, and then you need to know the knowledge of the length of the bar, which might change every time. Okay? So you can say, okay, I know that I get a pulse here, then it goes on, it goes off after the bar leaves. And yes, but I don't know exactly the length of the bar. So there are a lot of problems. One thing you can do is to measure the temperature from the bar. Okay? So you have two thermocameras. We will study thermocameras next, I don't, maybe lecture 11, something like that. And again, you can say, okay, I take the temperature here, I see that the temperature rises, then I see that after the bar goes on, the temperature drops down, and of course I have this speed. What we want to do is do a measurement which takes much less, so it does measure directly on a section of the bar without waiting all the bar to go on. Okay. So what we do, instead of using one thermal camera, we use two thermal cameras. Okay, and they are displaced by a distance delta x. So you have two thermal cameras, you have two signals coming from these two cameras, and you know that they are measuring basically the same signal, but they are measuring this signal with some delay of time. Why? Because the first camera is here and the second is here. So if the velocity is in this direction, I will see a signal corresponding to the profile of this temperature of this device, of this bar, from first on the signal on the camera 2, and then later on the camera 1. This signal might be noisy, okay? Because locally there could be some part of the bar which are already cooled down, which is already cooled down. There could be some impurity, so there could be all sorts of noises here. So you don't expect to see the signal 2, to see the signal 1 as an exact replica of signal 2, just shifted by 5 seconds. There could be a large noise. So our purpose is to check the signal from the camera 2, the signal from the camera 1, and find out how delayed they are in time. If you manage to find out the delay in time of these two signals, then all your problems are solved. Why? Because you know that between the first and the second camera there is a delay of 5 seconds. You know the distance, for instance, 50 centimeters between the first and the second camera, and therefore you can calculate the velocity there in that particular moment. Okay? You know the delay in time, you know the distance of the camera, you can recalculate the velocity. The problem, as I told you, is that, well, the advantage is clearly that you can do it without waiting all the bar to move, okay? Because you might have here some part of the signal which change, some part of the temperature which changes in along the profile of this bar, and you can use these changes to see the delay between the first signal and the second signal. Okay, so our purpose is to find out the delay between the signal coming from the camera 1 and the camera 2, even if these signals are buried in a large noise. How do you do it? You use the convolution. Probably you are very expert in that, so I will not spend much time, but just a reminder how to calculate the convolution. Let's say that you have two signals. In this case, I have sequence A and sequence B, and they have both 5 samples. This is oversimplified. Typically, you have a large number, much larger number of samples, but this is just to show how to calculate it. So what you do, first of all, is to flip. You reverse the sequence B, okay? And then you start your journey. So what you do is to take the first sample, multiply times the second sample, and you get 1. 1 times 1 gives 1. Then you multiply, you shift the second sequence and you get 2 samples overlapping. 2 multiplies 1, and you get 1, and you get 2, of course. And then 1 multiplies 1, and you get 1. You sum up together these two numbers, and you get 3. So at the first step, you have 1. The second step, you get 3. Then you make the second process, the same process after shifting another step. So now you have 4 times 1, 2 times 1, 1 times 1. So you get 1, 2, and 4, and you get 7. You move another step to the right, and now you get 4 times 1, 2 times 1, 4 times 1, 1.1, and 1 times 1, and you get 11, and you continue. Now you are in the middle, so you get 16. Then you move another step to the right, and you get 22. Then another step to the right, and you get 13. Another step to the right, and you get 6. And finally, the last step, which is 2. Okay? So once you get these two sequences, you take the sequence and you make it shifting step by step under the other, and you multiply all the samples which match, and you sum the results of all these multiplications. Okay? And this is the result of the convolution that you get by making this process. Now, most likely you will have a peak where you have most samples facing each other. So it's very wise to divide and take the average of that. So what you do is to multiply. In this case, we got 22 here when we were facing 1, 2, 3, 4 samples each other. Then here you have to divide this 22 by 4, because it's not fair. Let's say I will use some not very technical word, so forgive me if I try to simplify something in my lectures, but it's just to help the comprehension of what I'm trying to explain. So it wouldn't be fair to say that this is bigger than this one, because clearly this is obtained by multiplying a larger number of samples, or to sum larger number of couples which multiply each other. Okay, so it's not fair to say this is the biggest. So what you have to do is to say, in average, how much is one couple of samples which multiply. So here we have 3 couples which multiply. Therefore, it's just fair to say, okay, I sum, I get 13, but I have 3 of these samples, so I have about an average of 4.3. Here, I have 4 couples giving me 22. So just to be fair, we divide by 4, okay? Because it's clear that we get larger numbers than here, because here you have only 2 couples. But, okay, so now in order to be fair, you have to divide it. And you get, well, in this case, the peak is always here. But generally speaking, you get a profile where you find a maximum value. That maximum peak, that maximum value, corresponds to the point where the two sequences are the most similar. Let's make an example. Let's say that we have 2 functions here, okay? These functions are somehow similar. They are not exactly the same. You can see that there is a peak here, then it stabilizes here. This one goes down and then up again. But they have a large amount of noise, you see. This could be some non-negligible noise to be considered. Now, what happens if I calculate the convolution between these 2 functions? You see that you find a peak here. This peak will tell you when the 2 functions in this process, when you match one function with the other, then if you are facing one function to the other function, in the moment where they are very similar, then you have a spike in the result. It goes up. Okay? So here the peak is more or less in the same position. So you get the peak there in the center. Here at the extreme, it's in the position where the two functions are far away. So consider that here we have 400 samples for both curves. So 0 corresponds to minus 400 when the two functions are far away at the beginning of our journey. 400 samples here in the middle corresponds to where the functions overlap in the middle, and then 800 or 799 when at the end of the function, the two functions are again displaced. Okay, so let me just clarify this point. When you have the first sequence A and the sequence B, this corresponds to 0. Then sequence A, sequence B overlapping 400, and then when you have A and B, that's at the end. Okay, this is our this is how to understand the value here. So that's why here I wrote at 0, which corresponds to 400 samples. You can alternatively write minus 400 here and 0 here. Okay, doesn't change anything. Now, you see that the peak here is more or less in the same position. So you expect to find a peak in the result when the two functions are one overlapping to the other in the middle. So at 400 samples, as we have here. What happens if the first signal moves slightly to the left? Again, we have one peak here, then it goes down, stabilizes. Here the peaks are not overlapping anymore. You see, there is a difference. It's about 100 samples difference. You make your calculation again, you take the function, you make it flip every step by step. And what you see is that the peak now moves to the left about 100 samples. If you take the second peak and you move the second function and you move the peak to the left, then the peak of the result will be here, to the right. Alternatively, you can say that you take this peak and you move it to the right. It's the same. So, watching this function here, you can identify where is the maximum. And this maximum tells you how many samples of delay there are between the first and the second signal. Okay, so here we have 0 samples of delay. It means that they are the most similar when they are overlapping, just as they are. Here it means fine, we have the peak at about minus 100 samples. So if I want these two functions to look the most similar, I have to take this signal here and move it to the left, or to your screen, to the left, by 100 samples. If you take this function and you move it here by 100 samples, again, they will look similar. On the other way, if I have plus 100, well, this is not 100, this is maybe 50, something like that. And if I have 500 samples, let's say 50 samples to the right, I have to take this signal, move it to the right, and then this peak will match again this peak. let's see. This is the important part. First of all, this is not limited to functions which have one peak. Here I made an example with two functions which have like a sort of periodic behavior, like some sign, something like that. But generally speaking, it could have any shape, the waveform. Previously, I explained to you, okay, look here, you have one peak here, one peak here. So if they want, the function must be similar, you have to move this function to the right about 50 samples, something like that. But this is just an example. The function, the signals could have the shape you want. They don't necessarily need to be with some peak. They could have a function, for instance, like this one, where you have multiple peaks, multiple valleys, or generally speaking, not even a peak, just some strange shape you prefer. In both cases, you will have this function giving you the maximum peak here, which tells you how much of shift you have between between one signal and the other signal. So this method gives you the similarity, or better, gives you an information of how much you have to shift to one signal to get it similar to the previous one, to the first one. Okay, you have two signals, and I tell you, move it by 50 samples, and they will match each other. So it works not only for functions with one peak, but even any type of shape of functions or signals. But then, what is the advantage of this method? Because, as a matter of fact, you could use also a threshold, right? You could say, okay, so I have, let's say, you have this signal, you have this other signal, and then I say, okay, I decide that I take this threshold, well, not very similar, but it doesn't matter. There could be also some deformation between one signal and the other. Okay, they don't need to be exactly similar. As a matter of fact, it will work even if there is some deformation of the signal. It will tell the most similar they are, the higher will be the peak, and it's easier to identify the maximum. But generally speaking, so you say, okay, let's say that here I cross 0.5, here 0.5. This happens at time 1. This threshold happens at time 2, and therefore I can identify the delay between these two functions by simply calculate the difference between T1 and T2. That's the very same thing. Here I know that there is some delay, so I can shift by this delta T. And I know that they will be similar, the two functions. Well, not exactly, first of all, because you only watch this rising point, but this doesn't mean that it's exactly, is for sure the crossing of the threshold which we are interested in. There could be multiple crosses of the thresholds, and maybe we are just taking the wrong one. Nevertheless, the most important thing here that you notice is that by taking the convolution of the two signals, by making this process here, we get rid of all this noise. you see here, in the first signal, you have a lot of noise. In the second signal, you also have a lot of noise. But then, in the result, you get rid of all this noise. And the reason is quite clear, because if you think about that, here you are taking the sum of the products of multiple products. So if you have a noise, here you have one couple which gives a little bit more signal, another which has a little bit less, and so on. Each couple, if there is a noise, will give more or less contribution than what they would give if they had no noise. But then you sum them together. So the positive and the negative contribution given by the noise, they will even out, so that on a large extent, when you have a large number of products, then at the end, when you sum them together, you have you get rid of all these variations, because each contribution, positive and negative contribution given by the noise, will cancel each other. What it means? It means that here it's way easier to find the peak. Yes, sometimes the maximum is not very steep. Okay? So you could have a maximum like this, or you could have a maximum like that. And here it's more difficult to understand where is the maximum. Here it's easier because it's very narrow. So it's not so trivial when you have this result. Nevertheless, it's way easier than watching these two functions and determining the delay from these two functions. As an example, look at these two, signals, okay? You see they are similar, but I would ask you to tell me how much is the delay of signal 2, or better, of signal 1 with respect of signal 2. Generally speaking, if I watch these two functions, I wouldn't be able to find it. I see that signal 2 comes a little bit earlier, because I see that the peak is here, and here is a little bit later. And also this second, I don't know if I can call it peak, but higher value region arrives a little bit earlier than this one, if you watch it carefully. But generally speaking, if I have to give you a number, I wouldn't be able to tell you how many samples of delay the signal 1 has with respect of signal 2. That's very difficult to say. On the other hand, when you watch the convolution of the two signals, here you have a peak here, a spike, and here it's very simple to find that number of delay of samples of the signal 1 with respect of signal 2. It's in fact very simple to see. Here, in fact, the function is very narrow, so you can go there and say, okay, it's here, the maximum. Perfect. So this method allows you to see very well the delay of two sequences of measured data, which is something that you cannot do in time domain, let's say. When you have such large noise, it's very difficult to be evaluated. Now, what about using thresholds? Why is not a good idea? Because a threshold can be triggered before or later according to the noise. Here I took this sample signal that I was using before, and I artificially added some noise, and I ran 3 times the algorithm to create some random noise. So every time the system was creating some other noise, some other value of noise. The amplitude of the noise is the same. I always say that I want a noise with that standard deviation, but by being noise every time is generated differently. And I said, okay, I want the threshold to be at 0.5, and I want to check which is the first sample higher than the threshold 0.5. And in the first time I ran the algorithm, I got the sample 120. The second time, 108. And the third time, I got 64. Why? Because by accident, this time I had a sample which it was slightly larger than 0.5 due to this spike here, which arrived already at sample number 64. So if you watch the value which makes if you watch the time which makes the trigger, the threshold be triggered, then you get a number which is strongly affected by the noise. Because the noise can bring a single point by accident with a lot of noise cross the threshold and make the time 1 start. And then, of course, you have the time 2 where the measurement of time stops, and you measure a delta t which might change quite strongly according to this time when the threshold is triggered. So if you try to make a measurement like this, you will have a large noise caused by this. You will have a large variation of the time of delta t you measured by influenced by this noise. And it's also clear why it happens. Again, it's based on the fact that you are considering only one point. When you calculate the convolution of these two signals, you consider all the points, or at least the points which overlaps. Okay? So when you have the first sequence here and the second sequence here, at least in this region, you have a lot of points which overlap. And therefore, the noise is averaged out. What you are doing here is to take the information from a large portion of the function and use it to calculate your output. So you don't take the information carried only by one point. You take the information carried by a lot of points, which is more information. So therefore, here you get a much more precise measurement. Okay? Sorry. My microphone fell down. And generally speaking, if the two functions are maybe not matching, but here with a lot of points, you get a lot of information giving you the result. So definitely this measurement is better because it's based not on the knowledge of a single point, as you do when you consider the threshold. When you consider the threshold, you just watch the value of a single point and you compare to the threshold. In this case, we are considering the information being brought by all these points. So you definitely have more information and your result is more reliable. In this case, you just rely on a single point, and if that point fails because unfortunately in that point you have a lot of noise, then you the whole measurement is ruined. An important, okay, before going to the sensor of vibration, I hope I will have time this time. Yes, I think so. A practical application. This happened to me some time ago. I was working with some colleagues, and they were trying to measure, for instance, the speed of a domain wall. They had a microwire. It was pretty narrow microwire, maybe 10 micrometers. It was composed of a ferromagnetic material. So they had this microwire. They created a magnetic field H, which magnetizes the wire in axial direction. And then they have a domain wall. In that case, they have a single domain wall. So as you apply a magnetic field H, this domain wall propagates along the length of the wire, okay? So they were interested to understand the speed of this domain wall moving along the wire, okay? Because they were calculating some effort, they were using it for some sensors. It's not important. So what they did was to put a first coil here, a second coil here, and then they measure the voltage V1 and V2 given by these two coils. And they saw something like this on V1 and something like this on V2. And they were trying to determine the difference between the time when they have the first spike, which corresponds to the time when you have the domain wall crossing the first coil, and the time here when you have the domain wall crossing the second coil. Because knowing the distance between the coil, they could calculate the velocity. The problem is that this signal was very small. So they had a large noise due to the fact that they were trying to use a threshold here. But the spike here was rather small. So if you used this threshold, they had exactly that problem. Because if by accident here you have a slightly larger noise here, it made the trigger, it made the threshold be triggered before than in this point when you had actually the domain wall crossing. And the measurements were not so reliable. Therefore, I suggested them to use this method, to use the two, to take the two signals coming from the two coils, make the convolution, and then find the delay by using this method. And the results were much better, which tells you that sometimes it's not just a matter of the device that you're using. In this case, the device was the very same. They used two digitizers, or it was one digitizer with two channels. So they were acquiring the two voltages with the same digitizer, but it is the algorithm that you're using to extract the information which makes the result of your measurement better or worse. If you have the same device, you take the same measurements, so the profile of V1 and V2 are the same. But use the method of the threshold, you get a worse result. If you are using this method with the convolution, you are extracting all the information from V1 and V2, you find how much you have to displace them to be the most similar, and you get a better result. Okay? So be sure that sometimes it's not only a matter of using the best device to make your measurement. Sometimes what you need is always to take your data and make use of them properly to get the best results. It's not just enough to buy the best device. Okay? Now, let's go to sensor of vibration. I think I can do it in the last 5 minutes I have. What are we talking about? We want to measure some vibration. So let's say that we have a machine, it vibrates, and you want to measure this vibration. This is done very often, for instance, on mechanical machines to predict when they are getting, for instance, broken, because the mechanical engineers are very smart, so they can tell you that when they see some profile of vibration, maybe the shaft is getting broken, there's some problem, so they can detect some failure before the failure actually happens. And then of course they can prevent worse damages. But there are plenty of applications where you can measure the vibration. So here we have a system which symbolizes the device that we use to measure vibration. This is just a model. Okay, so we have a seismic mass inside our device, and it can move with respect of our device of a coordinate x of t. Then our device, the one which measures the vibration, moves to a reference point of y of t. Okay? So we take our sensor, we give it a vibration of y of t, and inside we have a mass which can move with the respect of it by a coordinate x. The total of the two coordinates is z. So you can write the equation of this mass in the coordinate z. Now you have the first component, which is given by the inertia of the mass, and it's proportional to the second derivative of the position of the mass at z. Okay. Then you have the damping, which is proportional to b. B is the coefficient of the damping. It means that here it's symbolized by this symbol here. It means that it gives you some force only if you change the coordinate. Okay. So if there is some speed of change of the coordinate, then you get a damping. And then there is a spring force, which is proportional to the displacement. Just take a spring, you press it, and even if it doesn't change the position, just for the fact that it's pressed, it will give you some force back. Okay? So the force that you receive from the spring depends only on how much you press the spring. The damping depends only if you gives you back a force if you move your position. So it's like if you move your hand fast, the faster you move it in the air, you have a damping of the air. Maybe it's better if you watch it in the water because the effect is larger. Okay. If you keep your hand stable, it doesn't have any force. But if you move it in a fluid, then you have some damping. And then, of course, you have the force of the mass itself given by the acceleration. So the second derivative of the position. Then you apply a vibration in a sine form. So you can write it as exponential of j omega t. And the solution will be another sine wave with another amplitude, x of omega t, and generally speaking, another phase, minus phi. Okay? So what we are doing here is to check x as a function of y. Why? Why? Because when we apply a y, when we apply a movement, a vibration to the device, we cause a change of x inside, which is something we can measure, and we will see tomorrow how to measure it. So what we do is to measure inside the sensor x. And from x, we can derive something about y, which is eventually what we want to measure. So if you take the amplitude of this, of x and the amplitude of y, and you take the ratio, and you consider psi as the normalized frequency, normalized to the reference resonant frequency. So here at C equal to 1, you have resonance. What happens? Well, if you have omega, you remember, is very small omega means psi lower than 1. Then this becomes, you have a psi which is very low, very lower than 1, so this becomes 1, because we have 1 minus something lower than 1 squared, so definitely 1, and this definitely is again psi squared, so lower than 1, so you have psi squared divided by roughly 1, so psi squared, which means that you have omega squared. Omega squared means that you have the acceleration. So you have here, you have an x which gives you the acceleration of y, because x divided by y, the gain of this device, will be proportional to omega squared. So here you have a part, you have a region where you get x, which is proportional to the acceleration of y, which means here you change y, and you get here an x inside that you can measure, which is proportional to the acceleration of y. For larger frequency, if omega is very large, then okay, seems somebody needs to come after me to have a lecture. Then this ratio, if you calculate, it's almost equal to 1, which means that it's this ratio is 1, so x will be proportional to y and not to the acceleration of y. Okay, so if I took 2 extra minutes than usual, and see you tomorrow. And as I told you, I will contact every one of you to discuss the results of the test. Okay, have a nice afternoon.